welcome back. Our next speaker is Nick Huggett, who's going to be speaking to us on quantum time and phenomenal time. Welcome, Nick.
Close enough, some more. The title's not totally apt now, but it's close enough. So I have a sort of couple of worries about the talk the way it is now, that it's sort of a little bit disjointed, I guess, partly because I had some ideas about what I wanted to talk about, and I've tried to focus on relating them to passage in a way. And it's also because of the audience, and the way it's sort of turned out, I think, is instead of having one talk for everybody, I sort of have two talks that relate to different people in different ways, and you'll see, there's a bit at the middle where they sort of join together, but they sort of don't join together as well. So basically, I think the first part of the talk is to sort of, I don't know, to talk to the physicists and psychologists a bit about some ways I see what's going on or has gone on in philosophical debates about flow, the flow of time, the passage of time, and to try and articulate. Hugh at the beginning talked about flow as one of the three things that kind of people try to add to the block universe to get to a different picture. Jeremy's talked about kind of the sort of broad-headed ways of trying to capture flow. I think there's another idea floating around in the philosophical literature, and I think it's probably the kind of picture that Chris was alluding to today, and I want to kind of say a bit more about what I think that idea is, though essentially sort of negatively. So the other thing I just sort of worry I have about the talk is some of the things I'm going to say strike me as really kind of pretty crude and maybe sort of obvious non-starters in a way. But I kind of sort of still feel, one thing that's been going well in this, I think in this discussion is people trying to understand the different things they might mean or have in mind by passage and flow. And even this sort of the crude things I'm going to say, I hope will help sort of define the logical terrain a little bit more, even if it's just by, wiping this whole big area off over here or something like that. But who knows, maybe people will actually want to defend what I take to be obvious non-starters, I guess, something like that. Okay, so that's the first part of the talk, is going to be talking a bit about how I think philosophers, hearing that, say, physicists want to incorporate passage into their physics, might sort of respond, and how I would respond. The second part, which is sort of the core part I had in mind from the beginning, is, well, it's aimed at the philosophers and physicists, psychologists, in two different ways. For the philosophers, it's sort of a piece of what you'll recognize as kind of scientific journalism, kind of a review of what time looks like in some approaches to quantum gravity. For the physicists, I don't know if it'll be very informative, and I don't know if I have anything very deep to sort of add to your understanding. So I ask you to think of it more as a sort of a big question mark with, coming with a big question mark at the end to do with, whether you think I'm presenting things on the right track, what you would sort of add to the pictures I'm saying and describing that might be useful for philosophers. But it's still just a very first sketch of what might be going on and things people might start thinking about. So, all right. I don't think there's any big conclusion here to sort of debate, but I hope there's a lot of fairly provocative things that I might say. So, let me put a kind of fairly strong picture up on a sort of clear sort of picture, sort of logically weak, but sort of strong in terms of clarity of what we're talking about when I think, I start thinking about time and like-minded philosophers of time sort of have in mind. Here's a kind of minimal model of how we should sort of think about time mathematically. And the idea is that time is well represented by the differential structure of the real numbers. Okay, this is sort of the basic picture. We've got the real numbers, and that really is what time is like, and you know, the real numbers correspond to, well, we think of them as points on a line or instants of time. We can go from there, and you know, that's just the minimal model. We could think that time also has a metric. There's a particular, you know, duration between any 2 points. We could form space-time by taking its, you know, Cartesian product with spatial dimensions in some way. That might be relativistic, in which case we wouldn't necessarily be thinking of producing, you know, extended instants of time. We might just be thinking about time along world lines. We'd still have that sort of minimal model embedded in there. I think we might even think that it's oriented. Indeed, you know, given what we know about nuclear physics, that seems to be the right answer. Though this is a physical orientation, and you know, as Hugh pointed out on Tuesday, this is not quite the same as sort of really giving a direction to time in a strong sense. But the laws seem to be, at least one of the laws seems to be time asymmetric. So as far as I'm concerned, and I think like-minded philosophers of time, these are just sort of elaborations of the minimal model into various, as I say, sort of classical models. And none of these amount to having, well, I don't want to say that. I guess the question I'm going to put on the table is whether any of these amount to having passage of time in a strong sense. And philosophers who claim there's a passage of time, I think, generally claim that this model does not incorporate, does not well represent passage. Physicists may mean something else, but I think when I hear people are arguing, you know, I'm thinking of the philosophical tradition about passage, there's got to be something else here. Raphael, does that answer?
A small technical comment. I think if the orientation of space of time is to be deduced from the elementary laws, local laws, then I think it's more correct to say that space-time is oriented, not
Okay.
time as such, because there's still CPT.
Right. Okay. Fair enough. Yeah. Okay. Right. Okay. All right. So, you know, said this is the basic kind of picture, classical picture of time. So philosophically, I actually think people the question of whether time is sort of continuous, has a differentiable structure, or whether it's atomistic is actually in a sort of in an orthogonal direction. But for a couple of expository reasons, I'm sort of assuming it's not atomic here. But I guess maybe I should say up front, I guess I don't think just merely making space-time atomic, you know, discrete amounts to introducing flow by itself. Okay, so look, so this is the model, so that clearly suggests sort of a program which is to sort of think about different temporal phenomena, those of physics, conceptual, linguistics, psychological, as we were talking today, and try and show that they too can be well represented in this model here. Okay, so for example, and this is sort of this example is partly kind of provoked by things George has been sort of saying, that in this model we have change. This is not a kind of hardcore, as I understand it, Barber type model. We really have different instants of time, and we have change because things are different at different times. So this is what also kind of goes by the name of sort of AT-AT, account of change. All right, so let's turn to passage. And sort of the big question then is, well, is passage sort of, you know, well, okay, we have to talk about what passage is. Some people, you know, it has been claimed, passage is not well represented by this, by current physics in some way. I guess that's what we're here to discuss, in fact. It's given the title of the conference. So that's what I want to sort of, you know, think about this program and consider passage here. And the idea is, right, that if passage is not well represented in quantum physics, in contemporary physics, then this might be an important clue to quantum gravity. And, you know, if this were the case, this seems to me would be a huge thing. So, just as a sort of little philosophy of science digression, you know, it seems like a lot of quantum gravity programs are interested in generating, you know, new predictions to distinguish themselves from classical physics. That's a much weaker kind of methodology than we've had in the past in other scientific revolutions. As various people have pointed out, Bob Weingart, you know, my advisor 20 years ago, you know, in other cases, we've been faced with a situation where there's some anomaly that we know about, some empirical anomaly we know about for existing physics that we need to explain. And that's just not what we have here. So maybe passage is that anomaly. Okay, so here's something pretty boneheaded to say, and I don't mean to sort of insult anybody because I think people, you know, certainly the physicists, are well aware of what I'm going to say here. So it comes down to what we want to do is think about what it might be for time to pass in, given the, you know, how we might try and represent the passage of time given this minimal model or its classical elaborations. Well, the kind of model you sort of think about here is, suppose I have a function, okay, and I'm interested in, you know, the limit of that function as the independent variable approaches some value. Well, you know, what we are kind of given by the differential structure, the classical picture of the standard picture of, you know, the real number line is the epsilon delta definition. For a function to take a particular limit as the independent variable goes to some value is to be understood in terms of the behavior of that function in finite segments, sort of, as we might say, sort of just before that value of the independent variable. Basically, it comes to this. The function has to have the property that you give me, let's see, any epsilon away from the limit, and I'll give you a delta such that the function is within epsilon of the limit for every, a delta away from the final value of the independent variable, such that the function is always after that, within that delta, within epsilon of the limit. But that's not a property of the point itself, it's a property of what the function does sort of in the finite regions up to the limit. And I think this sort of captures nicely a sense in which, you know, the at theory of what's happening in flow, or, you know, as independent variables change, really is sort of static, and it's the kind of thing that I think philosophers who are talking about flow really can't stand. Okay, and that's what they sort of are rejecting here. So this is from Courant and Robbins, you know, what is mathematics? They have a nice sort of discussion of, you know, how you should interpret the epsilon delta definition. Here I've sort of more provocatively rewritten it in terms of time. So here's a way you might sort of think, how did time flow up to the present? You know, if time flows, it must have flowed to the present, and the state of the world has kind of changed as it, you know, as it flowed. Well, this is how it's represented in our minimal model. Okay? There is no flowing. We're just talking about a property of how, you know, time approaches the limit. And, okay. So this is a, you know, this is a sense in which this is a very sort of static picture. Okay. Well, let me read on. I had these two quotations from Courant and Robbins to make the sort of point about the way in which, you know, you have a sense of flow, or it looks like you have t going to the present, but it's a sort of static picture of flow, maybe. They go on to say, register what sounds like a kind of not entire satisfaction with this definition. The epsilon delta definition leaves out something real to the intuition, and the rest is a quotation. But we think there's a dynamic notion of approach. There's something more going on than the epsilon delta approach, than the epsilon delta definition. It's not all quite coming up. It's an adequate mathematical framework for expressing our I think it says knowledge of the situation is how it goes on there. They feel there's something, this is just not adequately sort of dynamical here to how we think about things. And I think, well, two things. First of all, in the history of mathematics, you know, the significance of the epsilon delta definition is to give a rigorous definition of what it is to approach a limit when all other previous attempts had been in terms of talking about flow or dynamic movement of variables. And all of them failed. And this is the one that actually sort of succeeds. Okay? But second, this sort of feeling of inadequate, that there's something else going on, that flow is something more that we haven't captured in this kind of picture. Right. So, let me go, sorry, I hate it when people do that. So here's my sort of negative characterization of what I think philosophers often have in mind by flow. So trying to flesh out, what when Hugh referred to that term, offering, I think, a different kind of picture from the Broadhead kind of account of these things. Okay. But I can only do it sort of negatively by saying, when you think there's flow, you think that, when people claim they're a flow, when certain philosophers claim they're a flow, what they mean is this is not capturing everything there is about how an independent variable, how time approaches the present. What it is they think, positively instead, now that's a hard question, and I don't have anything positive to sort of say there. So let me just say, why might philosophers want more than just the kind of Broadhead account? Well, it's very, I think Jeremy gave 3 or 4 reasons about how you might sort of try and distinguish between, the sequence and the set of initial segments of the sequence, right? But I think most of them were sort of heuristic, and then you come down some sort of metaphysical picture that's hard to kind of, you start talking about, well, these things are real and these things aren't real, and it's very hard to know what's going on, I think, at that case. And I think, so people either explicitly or implicitly have in mind some stronger sense of flow, which is sort of captured by a rejection of this picture being sort of enough. Yeah. So, okay, that'll do. So, here's sort of some responses to this. So, Maudlin doesn't suggest rejecting the sort of differential structure of time. He thinks there's passage, and he thinks it's sort of a temporal orientation, either from the laws or right. A temporal orientation will represent passage. But he sort of faces a sort of similar kind of problem, right? It seems to be static in a similar sort of way to the epsilon delta definition. Okay, this is from Tim's book. We can have the lingering feeling that mathematical objects per se are not fit to represent the passage of time. Now, this seems like a very similar kind of impulse to the one that Courant and Robbins were talking about or making. But the apparent inadequacy must be an illusion. Everyone is perfectly familiar with the passage of time. Okay, I see what's happened here. Let me back up again, because I realize what's happened is it's cut off in a line of my slide previously. So I think it's better to go back and then pick up here again. The point I wanted to make that's supposed to come after the Courant and Robbins discussion is, if this is right, so if you followed that thought through, look, contemporary physics inadequately represents passage. And by what you have in mind by passage is something like what these philosophers have in mind, then it's not going to be enough just to change physics. You're going to have to change the mathematics as well. You're going to have to introduce perhaps something like, but that's a challenge. Maybe this is not a logical proof perhaps, but the mathematics we have now, flow is represented in this static way that doesn't capture flow. Okay? So if you want to build it into physics, the challenge is, are you going to need more, new mathematics and not just new physics in the same old mathematics? Okay. So let's sort of start thinking that through. And I've got the Maudlin making the similar kind of point. All right, so here's one thing you might say in response to Courant and Robbins. Okay, sure, the way we have of representing passage, either the epsilon delta definition or an orientation, it's static in the mathematics, but that's just sort of a feature of the way we represent things. I tell you this arrow or this epsilon delta stuff represents the passage of time. And since you, from direct experience, know what the passage of time is, you know what I'm talking about. And I don't sort of have to sort of pick things out anymore. So what I'm partly doing here is raising some questions about, something that seems to come up in talking about time is trying to distinguish, whenever we try and talk about time, especially when we do it sort of mathematically, we pick some representational framework, and there's questions about what it is to represent something kind of as hard, intangible as time. And, some of those have to do with what's surplus in the representation. Some of them have to do with what features of the thing we're trying to represent get left out of the representation. But, it's sort of a truism that unless you represent something by itself, there's always going to be sort of failures of isomorphism, right? So, okay, under some mappings. Okay, so here's one sort of response you might have, but this doesn't seem to me, I guess this was partly because of, George referring to Tim. If this is sort of the response, it doesn't seem, and I'm assuming, when I wrote this, I was assuming something perhaps stronger about flow than he actually, I think he maybe means now. If this is so I've got the case that the mathematics is simply, I'm claiming the mathematics is, as he seems to agree, sort of inadequate for capturing everything about flow. How are you you're still faced with this same problem about how are you going to incorporate that lesson into physics? I take it that what we're looking for, Tim specifically sort of proposes mathematically adding an orientation to time. I take it that we think, people who are pushing this line of thought think that a physics of passage in quantum gravity is going to take more than an orientation. And so Tim's sort of response to this problem of representation kind of closes off that discussion. He doesn't say, go find a better mathematical representation. So the one we've got is good enough. But I don't think it's good enough for, I don't think people think it's good enough for, a quantum gravity account of passage. Okay. Another famous attempt to sort of deal with this issue is McTaggart's. What it's presented as the minimal model is something like the plus an orientation is essentially, McTaggart's B series. And, McTaggart had the idea that, to understand change properly, we had to have something like passage. And to get something like passage, we had to have an absolute past, present, future division. Okay. So there was some discussion of this. I meant to write this out before. But just to be clear, I've said this minimal model, which is what I think I and like-minded philosophers sort of have in mind as competing to views where time has passage. It's a line. It's composed of all the instants of time. Or we can just think of a finite part and it's composed of those instants. Okay. And within that, we're perfectly happy. It seems perfectly possible to introduce a purely relative notion of the present. And I think its axiom must look something like this. Okay. So I have a binary relation on times. X is the present at y, and my relative present satisfies this. And unless you're giving me more than that, you're not doing what McTaggart wants. Okay. But what happens when we do more than that? Well, now I've got to pick I've got my line of times. I've got to sort of pick one of them to be the absolute time. well, I guess there's two choices. I can pick, well, three. I can sort of pick one of them, less than all of them or all of them, but none of those seem like viable options, right? I mean, if only one of them is the present, then it seems like then we have Barber's picture. There's just the present. If I make all of them the present, that seems sort of incoherent, and equally if some of them are the present. Okay? So, again, I'm sorry to put something up so crude, but I just want to have, like, really explicitly, I think, what people, who have a sort of how people who, something I do, a sort of non-flowy picture of time, how they're willing to incorporate the present. Okay. But we don't get passage for the reasons I just said. Okay. So here's a bit of a challenge, and we've heard, and it's good because we've heard various people, especially David on Tuesday, and Chris today, sort of filling in the details of this claim. But look, here's what I think. Personally, I think that, okay, I'll just read it. The broadly empirical criteria for passage, that I understand. We have a sort of conversation and people say, oh yeah, you experience this in passage or that in passage. And I was like, okay, I understand that. So I might make things we might sort of fall under this broad sort of heading. From me to, the other side of the room feels, or, from me to the, let's say, to the moon or something feels very different from, from me from a minute ago to now. I mean, we just experience things differently. Okay? We experience, motion is an example of that as well. The experience of things varying over time is sort of profoundly different from the experience of things varying over space, I think. Okay. Causes precede their effects. There's something else that you might think of has to do with passage, and I have a sort of empirical understanding of what that is. Okay? Or that things change. I already sort of said how that works. Because of the kinds of accounts we've been hearing here, I think it's, plausible that all those things are well represented in the classical model. Okay. All right. Well, let me try and sort of open things up a bit here, though. Maybe I'm wrong, and that seemed, maybe Tim's changed his mind now, but certainly in the book he seemed, at an earlier time was pretty insistent that, I think people were by refusing to sort of see something beyond this kind of list of things that can be accommodated in the classical model, were just sort of in denial about what they were experiencing. Well, let's suppose, I don't know, so maybe, there's some sort of, some kind of cognitive failing on my part that I'm not recognizing what it is he wants to point at. Okay, so, I did write this paper thinking, when I was writing it, I was thinking very much about Lee Smolin and his sort of talks I've heard him give on this subject. Whereas I sort of set things up at the beginning, it's very much to do with, look, here's some items of experience, and these have to be, these are experiences of passage, and these have to be kind of accounted for in quantum gravity. So I sort of realized from the discussions now that there may be other less experiential reasons for thinking that you want to build passage in some way into quantum gravity. Good, we should talk about those. I'm just explaining where I was when I wrote this paper, when I wrote the talk, and this seems like a real, serious suggestion we should be thinking about. Okay, so for the sake of debate, I'll say, okay, Tim's right. There's some sort of aspect of my experience which is passage, and I'm just not kind of picking up on it, and it's not properly, captured by, it's not properly analyzable by the classical model that I have. It's still represented by it, but there's sort of features of it that, somehow don't get captured. Okay, all right, so now let's think, how could one use that, right? These direct experiences of passage to build quantum gravity. I've already suggested that we'd have to come up with new mathematics, not new physics, if passage is understood in a certain way. Here's another kind of a point that I think Chris made today and we heard yesterday as well. What we're sort of saying here is, look, there's some feature, this passage, which our minds are susceptible, are sensitive to, And nothing else that we know of is. Not even our brains sort of thought of at the kind of neurological level. As far as we know there's no process in the brain that seems to depend on, at the level we describe it, that seems to depend on passage. Maybe at the quantum gravity level, our brains are the things that our brains are composed of are sensitive to it. But really, it's just our sort of minds that are sensitive to it. That seems really kind of remarkable, I guess, and a tenuous sort of thing to, build physics on. Okay, but, maybe that is the way things go. There's some sort of direct route from quantum gravity up to our minds that we can sort of build into the theory. Yeah.
Just point out the obvious that, the physics of brains involves like timescales of 30 orders of magnitude larger than the Planck time. The brains do not live in highly curved regions of space-time and so on and so on. So there's absolutely no coherent reason according to accepted physics why quantum gravity will have anything at all to do with the physics of brains.
Well, I'm trying to be sort of sympathetic to this idea, so I'm kind of glad you made the point instead of me.
In terms of dimensional analysis, it's absurd by as many as 30 orders of magnitude.
So, I mean, this sounds grist to my mill. I think that's fine, but I'm trying to be sympathetic, so I'm. I want to open up sort of see if we can have the discussion. So, I don't think so. But maybe it is worth jumping in at this discussion here. I don't think I'm almost certain Tim does not think of this as part of his argument that we should be going from phenomena of experience to some theory of quantum gravity. I think, at least when he was, I don't know what he thinks now, but in the essay that we've been talking about, his idea is that the passage of time doesn't have something to do with just physics, but somehow with the mind-body connection. Okay, and so that would be a kind of different way that it might show up. How quantum gravity might, again, he's not trying to suggest a program for quantum gravity. Far from it, I think. But if one was going to run with that idea, how quantum gravity might get into the mind-body problem, well, some people have suggested it, but that's a tough one. All right. So I've sort of given reasons to think that there's some, how hard this program sort of is. I wish it was sort of better news. As I said from the beginning, it would be really great to find some anomaly for existing physics here. Okay, but look, maybe I'm wrong. So, maybe it's okay, we can fix the math, we can find some physical clues in experience. Okay. So this is where the slightly dodgy bridge to the second half kind of comes in, okay? We looked at McTaggart, and he tried to add something to the minimal model, and it just doesn't seem to be coherent. Okay, I guess that's a bad way of putting McTaggart. It's his argument that you can't add something can't add something in a coherent way. Okay, so that's what he showed, I think. Maudlin, in a different way, says, look, we can add an orientation, but I'm happy to do that anyway. If that's all you mean by flow, then I don't have any problem with that. If it's an orientation in the sense of, that we can have in time asymmetric laws. But Maudlin seems to say, there's something this is failing to represent in, sorry, not that's failing to represent, there's something that an orientation fails to sort of analyze or kind of capture in our experience, although it represents it just fine. So, okay. So here's the dodgy bridge. Adding stuff doesn't really get us what we want. Maybe we need less stuff and maybe build on from there. So the second half of the talk, well, it better not be half a talk, I guess, at this point. The final third of the talk, it's going to look at some proposals in quantum gravity that in some ways offer weaker structures than this classical picture. And at this point, I have to say, do these represent passage? I don't have anything very deep to say. The kind of project I actually have in mind is trying to understand, sort of looking at models of simple toy theories, theories as they're as well developed now of quantum gravity, and trying to understand their empirical content. not generating novel predictions, but how they relate to the things we recognize in the world at higher levels today, especially time and space. I don't have time now, but I have sort of philosophical reasons for thinking that's the kind of project that philosophers of physics, or one of the kinds of projects that philosophers of physics should engage in. Okay. All right, so that was my sort of philosopher lecturing to the physicists a bit and psychologists. Now I'm the scientific journalist lecturing to the philosophers about some things that you may not know about and might be kind of interesting to talk about, and asking the physicists, especially if they have sort of, tell me if they think I have, I'm in interesting directions, if I've missed interesting directions, if I'm just hopelessly off in the way I'm thinking about these things. All right, so here's sort of 5 things you might think of to kind of weaken the classical model in some ways. Some of them won't weaken the minimal classical model, the mere claim that time has the differential structure of the real numbers, but some of them will. So I started about 5 past, right? Is that it?
Yeah, so we've got about 25 minutes, including discussion.
So if I do another 10, something like that. Okay, good. Okay. Okay, we might sort of say, okay, what if there's not a Lorentzian metric? What if space-time has conformal symmetry? We'll talk about that. Sort of related, what if there's, the manifold doesn't have a metric, or rather, time doesn't have a metric, time isn't differentiable, and also, what if it doesn't commute with space? Okay, so these are sort of possibilities which seem fairly radical, of varying degrees of, radical variation from the classical picture. So, first, what if we just go to non-Lorentzian space-time? Which, one thing you might do is sort of just have a Newtonian structure. Okay, I'm not sure of examples that are good to sort of discuss here, and clearly that just leaves, if we're just talking about some kind of Newtonian space-time, we're really leaving a lot of the classical model intact. So let's sort of pass over that. Here's an example of,
Just a question. When you say classical, do you mean non-quantum?
I'm sorry. Yeah, I mean just.
Pre-relativistic.
Well, I hope I said Newtonian when I was talking about the space-time. When I'm saying classical, I just mean in the sense of the classical models that I introduced at the beginning. Yeah.
Because time has a lot.
So it kind of cuts across the relativistic. Yeah, it doesn't map onto relativistic versus non-relativistic, and it doesn't map onto quantum versus non-quantum. Because time isn't quantum mechanical in quantum mechanics, really. So I don't know. I mean what I said on the first slide. So here's a sort of non-Lorentzian kind of interesting kind of case. And this is one where we have a non-commutative spatial geometry. So x times, x times y is not the same as y times x. All right, how could that be? Well, the first thing, very quickly, the first thing you have to do, okay. Oh, I see. I think, good. There wasn't supposed to be a transition there. Okay. All right, so there's my sort of xy plane there. Really, the first thing you have to do is just, really my transition should have gone the other way and the plane should have disappeared, because what you have to do is forget about the plane and not try to think of this in terms of the plane at all, and think about this purely as an algebra. I mean, cognitively, I want you to abstract away from the plane. If I was going to push a physical interpretation, I actually would not think of the algebra as abstract exactly. Okay. So let's just start with the commutative case. It turns out that you can specify, you can basically do geometry, ordinary commutative geometry, algebraically. So the very simple story is, you start, we'll talk about the plane, for instance, and so we have the x and y coordinate, okay? And you think of all the fields you can make that are polynomials in x and y, okay? And they have an algebra. It's not a very exciting one in the commutative case. because x and y commute, so everything commutes. But basically, if you have that, you've got the differential geometry of the plane. More than that, in this algebraic framework, you can introduce algebraic versions of all the sort of familiar objects. It's not too, if you're familiar with differential geometry, and we know, a derivative is essentially characterized by, defined by satisfying the Leibniz law for, for derivatives of products. It's not too hard to imagine that you can define an algebraic object that satisfies the Leibniz law. And a case people might be aware of in this still in the commutative case, is something that John Ehrman brings to the fore in World Enough and Spacetime, the idea that one can just have an algebraic representation of general relativity based on work by Robert Garrosh. That there's a way of just saying algebraically what's going on in a model of GTR. And, Ehrman's point was there, by going to the algebraic level, you're effectively quotienting over whole diffeomorphisms. Perhaps. People disagreed. Okay? But once you've got the idea that you can do away with the manifold in the commutative case, just do everything algebraically, it's a very natural thought developed by a lot of people. Alan Kohn, I guess, is the big contemporary guy. That one could do the same. One can simply deform the the commutative case to a non-commutative case. We'll just have an algebra of polynomials in the coordinates, but this time we'll set it so that they fail to commute. All right, so this is the sort of simplest kind of case. And it's a beautiful thing. You're not stuck with scalar fields. You can have gauge fields. You can have the whole framework of Lagrangian mechanics, all worked out in the non-commutative case. And it has many sort of mathematically, physically beautiful features. Okay. And you can do physics with it. The way you do physics with it quickly is you actually go back to the plane and introduce a new multiplication, not the usual one, according to which, so you just think of this as a new binary operation on the coordinate fields primitively, okay, and which fails to commute. Okay, and then you can press into service, or then people press into service the regular sort of framework of quantum field theory, just rewrite everything with your new multiplication, solve your path integral, calculate your scattering diagrams. 2 comments. Well, clearly this deformation, this theta, is an area. It's an invariant area, so not surprisingly, this theory turns out to not be Lorentz invariant. Interesting questions about how hard it would be to detect that failure of Lorentz invariance. Okay, from the point of view of our discussion, this is not so interesting because we still have regular classical time, as I've sort of talked about, as I've defined it above. There's only non-commutation between the spatial coordinates. I sort of mentioned this example partly in part to set up when we come to the more interesting case of non-commutative time. And talking of time, okay, I had some longer comments to sort of make here, but let me just say very quickly. String theory. Here's what Witten says about string theory. This was back in the late 90s. One does not have space-time anymore. This is Physics Today, he said, article. One does not have space-time anymore except to the extent that one can extract it from a 2-dimensional field theory. So what I've written down there is the Polyakov sigma action for string, for the non-interacting bosonic string. And I put that there. It's basically the same equation he puts to make this point. So what we have is the string. It has a time, we can place, it's a 2-dimensional world sheet. We can place time and space coordinates on it. What string theory is interested in is, given a coordinatization, and I now give you a particular, pair of coordinates on the string, Where in big space is this located? Well, that's X, that's my big X here. Okay, that's this, because I'm going to assume I have coordinates at the big space-time. So from the point of view of the big space-time, it looks like I've told you all the points of the string in that space-time. As it were, from the point of view of the string, it looks like that X field, for however many space-time dimensions there are, is a d-dimensional field on the string. Okay, so I had some comments about what the value of making this sort of picture is. As you'll see at the end, no, you won't see at the end because again it's cropped off the bottom. So let me say something. Should fill in some details. What's interesting though is the string coordinates, not surprisingly, have almost no physical significance at all. And although the action, I should have a pointer, contains this h, which is a metric on the string in terms of those two coordinates, the theory is invariant under diffeomorphisms, but also under rescaling. So if you push, sorry?
Theory on the world.
Yes. Well, it's
not string theory, just a theory on the world sheet. The string is
I don't know what.
two-dimensional field theory.
So let me say it another. I think I'm agreeing, but let me say it another way. Right? It's conform. So it's symmetric with respect to conformal. It's conformally symmetric with respect to the metric on the world sheet.
Yes.
Theory on the world sheet. I don't know. Yeah. No, it has conformal symmetry with respect to the world sheet metric. So if you're really going to take Witten's picture seriously, that is a kind of interesting result for time. You sort of have a theory where so conformal symmetry means it's symmetric under rescalings of the time. You sort of have a world in which time has no particular duration. Okay. On the other hand, there are some objections you might make to this picture. Even if you sort of address those, I'm sort of left with the feeling that there's some kind of it's sort of window dressing that's not really giving you any deep physical insight. All right, I'm definitely going to skip right over causal set theory. And in, 1 minute, since I'm already over, move to the final case of non-commutative space-time. What happens if we take not two of the spatial coordinates to fail to commute, or be non-commuting, but take space and time? So basically, the same sort of framework can be put into place, but here something pretty drastic happens to time. I don't have any deep conclusions to draw about it. It just seems an interesting topic. The first is when you work through scattering, you find scattering processes, according to Seiberg and his collaborators, backwards causation. Particles start scattering off, appear before the scattering event. The scattered particles appear before the scattering event. You also find worse sort of non-unitary evolution, which I've seen explained, though haven't seen this explanation justified in terms of saying the evolution at a time depends on boundary conditions at the past and the future, is what's going on. In this case, we still have a time coordinate, so we still have time in a sense, but we've broken quantum mechanics. Usually these authors, I guess coming out of their tradition, take that to be sort of the death knell for this kind of program. The very small aside comment would be, I guess you're looking for a theory of quantum gravity, but the failure of quantum mechanics itself ought to be somewhere on the table. One last thing is that I don't really fully understand. While non-commutative spacetimes violate unitarity, there is a sense, and this is what I don't fully understand, to say the least, don't fully understand, in which string theory induces a spacetime non-commutivity, not just on the string, but on the background spacetime, and yet is unitary. And I don't quite understand how remotely understand how to
Are those
reconcile that.
both within the same?
So let me just wrap up, okay? Because that is the last slide, and I need to. Anyway, all right. So let me just remind you of the first part, which was trying to, talk a little bit about how I understood, what I think philosophers have had in mind sometimes by denying or by asserting the passage of time. And as for the rest, there's a lot for me to learn here, but I think there's interesting stuff. Thank you.
Thank you, Nick. Edward, you were in the middle of a question.
I was going to ask whether these two things are within the same, approach, phenomenology or whatever else string theorists use, because they're used with many different sorts of such, and there are very few cross-checks or compatibilities or even logical consistencies between what happens in different approaches. So, I mean, is that unitarity specifically of the non-commutation of Geneva, or is it applying to some other part of space?
It's to do with D-branes. It's got nothing to do with the space-time. It's the fact that when you're comparing products of D-branes, that is non-commutative. And then they have this claim that when you have enough D-branes, it warps the geometry around it. But you need lots. It becomes a black brane, to warp the space-time.
Okay, but
It's the D-branes, not the space-time.
it's specifically a model which has both non-commutation and unitarity at the same instance.
But it's not space-time, though.
But it's not a space-time.
Right.
I mean, right. So clearly, this is one of the things. Okay. So you think that's what's going on?
So
That there's sort of non-commutivity of kind of different things in the two cases.
D-brane non-commutation. You should say D-brane non-commutation rather than space-time.
Right.
That makes sense.
Carlo.
Nick, I'm a bit. You said you want to give a view to quantum gravity. You're leaving out.
Could you speak up, Carlo?
Yes.
Seems to me that this is a very
Sorry.
bad. Let me put it so. It seems to me this is a very bad description of what is quantum gravity, both because of what leaves out and because of what it puts in. It leaves out the majority of the papers on quantum gravity today. The number of people that work on quantum gravity, and it puts in things which, by description of what Descartes would do, is not quantum gravity. I mean, there's nothing quantum gravity that this sort of non-commutationality. So I don't think this is quantum gravity.
Yeah. Okay. I should have said this more clearly then. So that's totally fair. So let me make a couple of reasons that I would sort of deflect the criticism and then take a bunch of it on the chin. Okay. So first of all, when I was preparing the talk, I was thinking about who else was coming and what they would be talking about, and so I tried to move away. I didn't want to kind of duplicate what I took was going to be talked about. People working in sort of loop quantum gravity, causal set theory. I assume those are kind of some of the things we're talking about. But I figured other people were talking about those, so I didn't put these in. Yes. So taking on the chin a couple of times. You're right. I should have said that I didn't mean this to be in any way sort of all-encompassing of approaches. I think that's fair enough. I just thought that these were some that had something interesting to show about time. You're right. Even worse, I really shouldn't be calling this quantum gravity. But I'd be happy to call these approaches to quantum space-time. There are quantizations of space and time. Right, fair enough. There's very little gravity in most of what I said. That's absolutely right, and I really should have said that. But still, insofar as we're trying to think about other alternative structures for time, I think these have some suggestive things for people to think about. Yes.
Epsilon.
I submitted even before quantum gravity. Classical gravity gives you some encouragement to think about becoming in the following way. Einstein tells you that it is space-time tells matter how to move, matter tells space-time how to curve. So there are causal relations between matter and space-time. Space-time now becomes subject to causality, which means that causality is more primitive, more basic
But I take it as general relativity is completely compatible with the sort of minimal model of time that I put up, classical model of time that I put up here. So unless you're sort of saying, that's fine, you're just not disagreeing with me, right? You're just giving me a sense in which passage can already be accommodated in the picture that I gave you. But okay, but then what I'm saying, again, I'm sort of here partly reporting sort of philosophical dialectics. There are people who don't think that's an adequate representation of passage. Unless you're saying, wow, look, we can look at classical gravity and it has this sort of property of causes that somehow doesn't itself fit within quantum gravity, and so quantum gravity just logically has its own destruction within it.
Quantum gravity will come later.
So general relativity has its own.
It's first of all,
But are you saying
passage means that there is something more basic than space-time. Passage governs space-time. That's what everybody who talks about passage of time says, that this is something more fundamental. Now it is interesting that relativity itself, general relativity, tells you that space-time is not the most basic thing, but causality is more basic than space-time. Space-time is subject to causality. Doesn't that make the two, show you some affinity between the two views? Or am I missing something?
So the first thing is, right, so sure, I mean, I think it's become pretty clear that people can mean different things by passage, different things by flow. Okay, so I particularly had one thing in mind, and I don't think that's what you have in mind here. So partly what I wanted to do was get that on the table so people could say, no, that's not what I have in mind. But so let me see. This extra thing so what the structure that you're finding in general relativity, is general relativity adequate to express it, represent it? Because if so, that's the kind of view that I'm accepting.
It is adequate, but it seems to me that it raises so many new questions that invite you to keep searching. Well, I should be careful. One of the hallmarks of the crackpot, according to, I think it's according to Cook, is that whenever he says that relativity is a good theory, but there is no mechanism, it's very likely that he is a crackpot. So now I am declaring myself as a candidate for being a crackpot. It's a beautiful explanation, but then it tells you that there is something more basic going on beneath it.
That's okay, but look,
many points beyond itself.
Yes. First of all, by black holes. You agree? And that is my question now of this entire beautiful meeting. I mean, you guys come and say, do we need a passage of time or do we not need a passage of time? Perhaps you do, perhaps you don't. But we have general relativity, we have quantum mechanics, something very basic is missing in there. So that alone should suffice to say, let's listen with more sympathy to the idea of passage. Or am I wrong again?
no, but let me once again kind of situate what the talk is trying to do. I mean, in the sort of broadest terms. Here's one kind of notion. So here's one kind of notion of passage that I sort of set up earlier that I think is in people's minds in the philosophical literature. And the reason why I don't think that's going to work. Now, is that to say, right? Let's just focus on that part. Some reasons why I think that may not be. Thinking about that is unlikely to produce sort of results in quantum gravity. But I don't think at any point, I hope none of my words sounded like this, certainly none of the logic of my argument, as you just sort of demonstrated by counterexample, right, are to the effect that no reflections on passage can help with developing a theory of quantum spacetime or quantum gravity. What I'm saying is there's one particular kind of avenue that I criticize, and just to help discussion, I think, between physicists and philosophers, I think that's the kind of picture philosophers have in mind when they hear things like passage and flow. And I thought it would be useful to say that to the physicists, because I understand that's probably not what you have in mind, but to further sort of dialogue here.
So may I add just a brief historical comment? There was a famous meeting between Bergson and Einstein. The two admired one another. It was just a brief meeting. And it turned out that they parted with Einstein showing Bergson that he made some errors in the creation is more basic than space-time, is more basic than causality. And he tells you every time that you try to mathematize it, then you kill it. There is something there that the moment you try to make it spatial, and we are spatializing time, we are missing something. Now, of course, that sounds completely mystical, but with some, it does not? Good. So with some added rigor, with some added rigor, we may be able to do that. And this is
okay, but that just sounds self-contradictory now. Because it sounds like what you're saying is the point I was going back to, right? Okay, mathematics always kind of loses something to do with passage. Oh, so let's get some better mathematics. But that's going to also lose it as well, right? This is kind of my point.
Not
but then you're not. But then the thing you said at the beginning was
the way.
false, right?
I think
mathematics
what
doesn't
you say is that
necessarily.
the way today we've mathematized things kills it. I don't think that you say that there couldn't ever be some kind of mathematical rigorous.
I mean, then I agree. That's sort of a point.
Spatializing it is a necessary.
Okay. But this is one of the things I said. Right?
Think
That
about
we
Big
need
Bang.
not just different physics, but different mathematics.
Big Bang. Big Bang is something which is more fundamental than space-time, and it's still mysterious. Perhaps this is mysterious still keeps happening. I know it sounds mystical. There is some good science.
It occurs to me that the mathematical base in the missing is Tim Morgan. Yes, we invited him to come.
I don't think he'd appreciate
I wouldn't have said it if he was here. We'll have to wipe that. No, so what I'm going, as you know, there's a discussion period scheduled in the timetable. Dean and I are going to propose that we skip that because we've got after one more question for me, because we've got it's a hot day. We've got a bus at 12. There are sandwiches out there I can see on the table.
What time is it now?
It's now 6 minutes past 12. He also has been waiting to ask a question from the beginning. So
Just a practical question. Can we have time to run back to our rooms for a few minutes?
I'm giving you more time because most of us are going to be in each other's company all afternoon. So my proposal is that we as it were, move the general discussion onto the bus,
Right.
In order to give us more time now to settle down, change if you want to do that kind of thing.
No later than 12:45. I would say, but no later than 12:45.
Okay, so we want to be downstairs by 12:45.
Can you say when the bus will return?
I think we don't know because we still don't know whether we're going to be able to go up the mountain or not. That depends on what's happened to the wind. It seems to have got a bit windy.
Can we cold up there?
I think, if we do get up the mountain, it could be cold, so I recommend taking a sweater.
So when does the bus go?
Pardon?
When does the bus leave?
I think it leaves at 1. Be downstairs at 12:45, please.
And it's in front of the hotel?
Yeah, in front of the hotel down there. Josh,
Roughly how long are we going to be away from?
again, that depends on whether we get up the mountain, I think. So I think, a factor 2 or 3 days. I always say you can get up there and then we take the car shots and be up there for a week. Is anyone cool with that? Please, Josh.
Yes, I was surprised, perhaps even humbled, by the quotation you put up from Courant and Roberts. So maybe I didn't understand it at all, but I thought that quote was criticizing the epsilon delta definition of a limit because it employed notions like approaching or tendency that they said are not based in mathematics or could not be properly defined.
No. So you mean this piece down here? This is just a comment about, the first one's just a comment on the epsilon delta definition.
Yeah, it doesn't move, it doesn't tend to, or it doesn't approach in any physical sense. No part of the definition has a meaning by itself. That seems to be a criticism. So that surprised you. It seems to be a criticism of the epsilon delta definition. But the epsilon delta definition...
It's just described. It's supposed to be a description of the epsilon delta definition.
But the epsilon delta definition doesn't refer to notions of approach or tendency.
But again, I
you
think that
only need an existential universal quantifier.
Isn't that correct Hawking's point?
that's their point. They're telling you what the epsilon delta definition says, and it doesn't say that the independent variable moves.
It doesn't say the independent variable is time either.
No, I
So it could be any other independent
Sure.
variable.
Yeah. But they weren't talking about
Any
time.
other meaning, it could be a spatial direction, it could be some biological or economical parameter.
This is just a characterization of the epsilon delta definition.
General.
But when they say leave something out,
No, that's what they say afterwards, and then they're like registering some kind of intuitive dissatisfaction with it, something that doesn't
okay,
occur in the
So at this stage, I can feel the class getting restless. This class is always given as an excursion in the afternoon. So I think we should thank Nick at this point.
He's doing an uncertainty principle job, isn't he, on that bit? So say if you probe a string, it opens up, that's a separate one. But that's not space-time, it's not like non-commutative space-time. So there are people who say you get non-commutative space-time, but they mean D-branes have...
Right, no, it is the uncertain.
Right, yeah. So that's slightly separate from the kind of non-commutative space-time.
Right, but you think
so the D-brane
the uncertainty can be translated into a
sort of, because Veneziano says this as well. That,
that's
like a lengthy kind of thing going on, like a cellular almost structure.
Right. Yeah, I'm just going to set this back up.
It's sort of like a minimum
type
argument. So I'm not sure I would say it's non-commutative space-time, but it's like a space-time uncertainty.
I mean, he's quite right.
I don't know.
He introduced a I can't remember you're right. It is uncertainty. So maybe in the final one I should have slipped down to uncertainty.
Or mention the D-branes one, because there are people who say that you get literally non-commutative space-time from D-branes because they have matrix degrees of freedom. So when you take a string between a pair of D-branes, you've got products of matrices.
Right.
Which are obviously non-commutative. And then they say these D-branes have geometrical properties and they sort of warp space-time.